Hello, my name is Alistair and I will be presenting automatic detection of Nyquist ghosts in whole-body diffusion-weighted MRI using deep learning. I'd like to thank my co-authors, Anna Barnes, Stuart Taylor, and Zhang. I'd also like to thank my funder, the EPSRC. Although, in theory, ADC values should be consistent across scans at different visits or from different subjects, whereas not to be the case in practice, which is an issue when it comes to the use of ADC as a biomarker in oncology. One factor that can affect ADC estimates is the presence of artifacts in the constituent diffusion-weighted images, with one of the most prevalent in whole body being Nyquist ghosts, which affected more than 40% of the slices in our dataset. Currently, there is no method for automated detection of Nyquist ghosts in whole body diffusion-weighted imaging, meaning they have to be identified manually, which is a time-consuming process. So the aim of this work is to develop a supervised deep learning approach that enables the automatic detection of whole-body diffusion-weighted image data corrupted by the presence of Nyquist ghosts. Diffusion-weighted image volumes corresponding to the abdominal region from 22 subjects were taken from the streamlined dataset, resulting in a total of 616 diffusion-weighted image slices, which, following careful visual inspections, were assigned a binary label indicating whether they contained Nyquist ghosting. The mean percentage of slices containing Nyquist ghosting was 44.2%, with a standard deviation of 25% across all subjects. Class imbalance can have a significant detrimental effect on the training of classifiers, and there was a large variance in the quantity of Nyquist ghosting per subject in our dataset. Our solution was to have the subjects with the highest percentage of slices containing Nyquist ghosts be paired with the subjects containing the lowest percentage of slices containing Nyquist ghosts to try and limit the class imbalance in the training set during cross-validation. An 11-fold cross-validation approach was therefore utilized to train and test the network. The standard deviation of slices containing Nyquist ghosting across the image pairs was 5.3%, which is much lower than the standard deviation of 25% across individual subjects. Initially, no pre-processing was performed on the images prior to training. A second pipeline was then constructed where the images were windowed between intensities of 0 and 25. This was done for two reasons. Firstly, the maximum intensity of each slice varied considerably, and the intensity of the Nyquist ghost was typically less than 100, so it helped to reduce the variation in intensity ranges. Secondly, windowing the intensity values below 25 was hypothesized to help to prevent the network from overfitting to irrelevant features, as the center of the slices, which typically have intensity values greater than 25, ended up with homogeneous intensity values, effectively removing much of the corresponding features that are irrelevant for detecting Nyquist ghosting. A standard transfer learning approach was adopted, using VGG16 pre-trained on ImageNet. As previously mentioned, an 11-fold cross-validation approach was used. Each iteration, 18 subjects were used for training, 2 for validation using early stopping to prevent overfitting to the training data, and 2 to test the resulting model. The early stopping was set up so that if there was no improvement to the validation loss after 5 epochs, the training was stopped. To reduce overfitting and improve generalization error, dropout regularization was applied at a rate of 0.5 to the dense layer of the classifier during training. The test accuracy was reported as the percentage of test data assigned the correct classification label on the final model of each iteration. The percentage accuracy of the classifier on test data for each of the 11 cross-validation iterations is shown in this image, for both the network trained on diffusion-weighted image slices with intensity values windowed between 0 and 25, and for network trained without windowing. The mean test accuracy when trained on diffusion-weighted image slices windowed between intensities of 0 and 25 was 81.5%. Without windowing, the network achieved a predicted accuracy of 73.1%. A paired t-test found the difference in the mean test accuracies to be significant, with a p-value of 0.018. In conclusion, experiments on the streamlined dataset demonstrated the feasibility of a transfer learning approach to automatically detect Nyquist ghosts in whole-body diffusion-weighted imaging. Detection of artifacts whilst the patient is still on the scanner could allow for adjustment of parameters in order to remove them, allowing for a more accurate measure of the ADC. Thank you for listening.